I'd love to present today what we believe is sort of a maturity model for cost saving through technology. Feel free to ask any questions, as Christina mentioned. So I'll give like a short introduction of myself. So I'm Saf Ezra, as Christina mentioned, CEO and co-founder of Granulate. We do real-time continuous optimization, and we'll talk about that throughout the presentation, as well as other methods. So basically, to give just a context of everything around what we call cost optimization. So you can see that, or you're probably tired of hearing about cloud hygiene, resizing, automated operations, discount purchasing. So everyone's telling you, okay, so shut down your dev and testing machines when you're not using them. Everyone's telling you, okay, so you're utilizing just 2% of the machine, just resize it. Or this machine hasn't been touched for a few months, a few weeks, stop using that, just remove it, and so on. So we will not, at least I will not touch on that today. Our main focus would be sort of new approaches and what we call the new frontier of cost optimization and even performance optimization, because we believe that cost optimization is merely a side benefit of what we're all about, which is providing best user experience, best quality of service to our customers, to our users, while maintaining the highest SLAs. And maybe we can do that with less infrastructure or less costs, but basically everyone's running over provision today, not because they like the over provisioning, but because they have to abide by certain SLAs and so on. So if we look at what was happening in the past, so it started with a lot of best practices, a lot of organizations, and probably not digital native companies have done lift and shift methods of just running in the cloud. Everyone's spinning up their own machines. You write a new service, don't worry about performance. We'll worry about that later. And so best practices have been accumulated as to how to best utilize the cloud. And then the cloud providers themselves have realized that they're running at very low utilization. They have excess compute, so they came up with spot instances and preemptibles, or what used to be low priority VMs on Azure before the spots. And so on top of that, a lot of cloud management solutions have come up, and that's where the terms cloud hygiene has come from. That's where all the best practices of just shutting down machines at night and so on have risen. But in the past, let's say year or two, we have seen a new sort of what we call new frontier of that. That's due to increasing automation, increasing AI technologies that allows you to really dive deep into what your production system can do and what managing workloads can look like. So we call it workload orchestration and sort of infrastructure configuration. When we say infrastructure in this meaning, we mean across the technology stack. And there's also real-time continuous optimization, which we put alongside all three of those, and we'll explain why as we go along. So obviously, since this is we chose the axes, so we can see that we chose performance improvement and cost reduction. So it's really easy for us to say, okay, if we look at configuration tuning, which is something that no human can do today because we have too many knobs around all of our components, around all of our infrastructure, around all of our solutions that we already use, the possibilities are endless. So we have to have some sort of automated system, a smarter one to make the decisions instead of a human being doing that. And then we have workload orchestrations. So we have Kubernetes, we have companies like even Densify or Turbonomic, which say, look, you have a huge infrastructure, you have elastic environments? How do you know which ones do you need to use? How do you know which sizes of machines do you need to use? How do you know that you're using the right placement? If you're utilizing Kubernetes and you have different pods on the same machine, how do you know that you didn't create just something that's not complementary and they're competing for the same resources and so on? And so sort of manually looking at all of these in real time doesn't make sense because they change over time as traffic changes and so on. And we also deploy new versions every day, every week. So it's really important to have something automated to do that. But this touches mostly on utilization, so around the cost effectiveness and not necessarily about the performance. And then what we try to do about real-time continuous optimization is the ability to autonomously do performance optimizations that are based on the sort of restrictions that you apply to your machine and application. And what do you mean by, let's start to dive into all of these. Infrastructure configuration. So you can see that we have a huge stack, and it starts from the machines in the cloud itself, which resources. So for example, GCP users would know that you can vertically scale your machine. You don't have to choose from templates. You have your sys controls and your, for example, Linux machines and so on. So you have so many knobs to turn. You have so many possibilities that manually optimizing that makes almost no sense and could somehow get us to certain performance improvements at a certain point in time. But production environments change constantly. So we deploy new versions and we add new components, and another team has inserted something that we haven't used yet, and so on. So again, this has to be done again and again, and it has to be done not manually. So how a lot of companies are integrating solutions such as these into their own system. So they call it continuous optimization. They inline it with the CI/CD process. Basically, you have your you have your deployment, you compile your version, and then before you do all the integration tests and before you deploy it to the field, you add another step where you utilize that AI or that smarter decision-making tool to make sure that you can actually you can actually change the configuration. Only then you do the integration tests, and then you deploy your new version that's preferably optimized a lot better. And Christina, we're happy to share the presentation with the links so people can see what we mean by, I don't know, examples about the different improvements. And when we talk about workload orchestrations, we talk about the fact that we have to make decisions again on a continuous basis because traffic changes. So you have to increase the amount of VMs that you use, your pods, your containers, and so on. So we talk about a sort of cycle between provisioning my resources, placement of the workload itself, so the application. Again, this could be that I'm utilizing containers. I want to make sure that if I'm putting two containers in the same machine, I'm not causing any problems. Or if I have a pod that is unnecessarily large, unnecessarily small for a certain machine size and so on, I can increase my machine and then place another pod there and so on. And that goes with the sizing. This is sort of a feedback loop that is created. So it has to be done in real time, it has to be done over time. And why is that a necessity today? Because today, if we go back, a lot of organizations are not utilizing their machines to the max, because if you're running at very high utilization, you start degrading your own performance. And we'll see an example for that very soon. And so if you're running at very high quality of service, you might end up very low utilization, and you want to find that sweet spot. So this is exactly what these types of solutions are designed for. And I think it's, again, if we go back to sort of what we focus on in this presentation, so we want to focus on those solutions that are sort of low cost in terms of manually putting in effort and hard integration into those automated solutions that can provide real value really fast. And so if you're looking into the configuration tuning, you just add another step according to into your CI/CD. You put the right integrations of the components, and then you get a better configuration for your deployment. In this case, some of these actually work just by integrating them with your Kubernetes deployment, for example, and then they start to operate, first bringing you insights, and then when you move them to active, they can actually take on the actions and start optimizing both the sizes of the cluster and so on. So these are very low cost in terms of manual labor, in terms of the implementation itself, and usually very high reward in that sense. So what do you talk about when we say real-time continuous optimization? We focus on the part that's post-placement. If we said, again, provisioning, placement, and sizing, we focus on the post-placement size. We have our operating system and kernel. That one is in charge of CPU, network, memory, storage, distribution, and so on. So disk accesses, memory accesses. We have our application, and the application itself has certain goals. So right now, if we look at operating systems in general, most of them are aimed for interactivity and fairness. So we're built with a user behind the keyboard in mind. They want to make sure that if you're browsing the web, watching a webinar, writing a document, you can do all of them with no delays. But in your production system, those applications are running in containers or VMs or pods. Each of them has its own unique goal, let's say. So if you know that goal and that is happening every time, so let's say latency, let's say throughput. So for example, if I'm Zoom and all I care about is the amount of users that are getting the highest quality video, then I aim for network throughput. And I don't necessarily care about a lot of other things that I might be running on my machine, and not necessarily care about the fairness of everything. All I care about is the throughput. So if I know my goal and I know how to tap to the resource allocation, maybe I can measure what I'm seeing. So let's say a latency on a certain port, or again, the network throughput. I can infer the resource usage patterns because the application itself does it over and over again and at very high traffic. So I can do anywhere between tens of thousands of requests per second on a certain service, for example. While on this case, I can identify the right bottleneck, the right times that the machine itself that I'm running on is the bottleneck itself, and then I can optimize. And we'll do a small example just to make sure that it's easy. So let's assume that we're, for example, logging into Netflix. So Netflix doesn't want us just to say that, hey, we logged in successfully. It wants us to show us, okay, so this is what's trending. This is recommendations for you based on your history, and that's your list, for example. So we query our, let's say we query our list, we query what's trending, and we query what's new. And our list has been returned, and the trending has been returned, and we're still waiting on what's new. So what happens on this machine right here is that it's handling anywhere, again, between tens of thousands of requests at the same second. So it can do a lot of things, a lot of different things. But for this particular request that we focus on right now, it can only process data from the list, let's say, and the trending. So if we choose, instead of doing everything else that we can, to focus on, let's say, processing the data from my list, in this case, we're not really advancing this request because we still have to wait on what's new to return a response back to the user. However, again, this is not in idle times because we have a lot of incoming requests as well. A lot of people are logging into the same service, and they're waiting, for example, in this server right here. So these requests are actually blocking while we're processing that data if we do it in a larger scale. So not only we're not advancing this request right here, we are actually making all the other requests for which this server right here is bottleneck wait. And this all changes once the new things have been returned, and now we can return a response to the user. So now service A, in this case, the login server, is again the bottleneck for this particular request. And not only it's a bottleneck for a request that we can send back to the user and free up some resources and hence reduce contention. So, but we only know that we shouldn't choose this data that came from these services only if we're aware of what the application is doing in sense of when service A is the bottleneck for that. And today, the infrastructure, the underlying infrastructure, so the operating system kernel has no knowledge of that. And so it chooses what it does based on what's waiting. So if it sees that data is waiting, it'll process that with the same priority as it processes data that's incoming. And so that's why we have to make the underlying infrastructure more application aware to make better decisions. And basically, if we look at Granulate itself, that's what Granulate does. Again, the feedback loop of the analysis. Obviously, if we look at, in general, real-time continuous optimization solutions and Granulate in particular, since all of the changes are done in the underlying infrastructure, it's pretty much agnostic to all architectures. And so very much sort of orthogonal to everything else that in terms of initiatives of cost reductions. So this goes back to the infrastructure configuration as well and the workload automations. Okay, so in particular with Granulate, and again, this goes back to the other solutions as well, we're talking about, in this case, just installing agents that run on the machines themselves. So it's pretty much straightforward. And since you do everything within the same VM, you have a quick return. You see the value very quickly in terms of the changes, because everything happens repetitively over just the course of a few seconds, even tens of thousands of times. So the goal is known, the repetitiveness is there, and you can close the loop of the feedback by actually making the changes very quickly, starting in this case with a single VM. So we don't have to integrate with the CI/CD or manage the Kubernetes. We added a few examples of how it looks like from a customer standpoint. This is actually a Datadog screenshot that our customers sent us, and you can see how latency was dramatically reduced, and it's a lot more stable since the installation. You can see that in that case, they were actually able to reduce costs by about 75%. I'm happy to say that it's actually even better than the posted case study on our website, because they were able to achieve more over time. There's another example with a company called Startup, where you can see that they chose to sort of, again, this goes back to the performance versus cost. They chose to save about 1/3 on their cloud costs while remaining a lot faster in terms of giving responses to the queries that their API is producing. And basically, that's it about us. Real-time continuous optimization. These are just some of the numbers that we've been getting. And again, this goes back to the no-code changes. And I think this is the same for the workload orchestration and the infrastructure configuration optimizations. All solutions that you can implement today, probably pretty agnostic to all other initiatives that have already been implemented, and a pretty low cost in terms of the manual labor required to both implement or integrate with them.
Wonderful. Thank you so much. That was really helpful. And now we will introduce Ofer Adon, the CTO of Carbon Relay. Take it away.
Thanks, Christina. And thank you very much, Asaf. That was actually a great introduction for me as well. So, hi, everyone. My name's Ofer. I'm the CTO at Carbon Relay. I want to talk to you a bit about optimization on Kubernetes specifically. There's a few things which are actually a fantastic complement to the things Asaf just shared around AI ops, how we do optimization, how do we think about optimization, and sort of what is the next step for all of us, specifically on Kubernetes. So for those of you who have developed applications on Kubernetes or are trying to get into the Kubernetes world, you know that there are a few hurdles when you get started, right? Cloud native is not simple, or the mindset is not simple. Kubernetes itself is not simple. And sort of the third hurdle there is getting your applications to deploy reliably and to even understand how your applications need to be configured before they go into production. So I'll start off with a very simple example. We're going to be talking specifically on the CI/CD pipeline, as Asaf mentioned. You know, today we're going from the traditional CI/CD into CI/CD and continuous optimization. But when you start off and you have your application, you've tested your code, you have your unit test, you may even have your integration test, and you go and deploy it, and say for new Kubernetes users, nine times out of 10, you will not be able to deploy reliably. You'll deploy and it will crash, and you'll have to go and figure out why. As Asaf mentioned, I'll show you in a second, the process as it stands today is incredibly manual. It's incredibly time intensive. And I would say it's not incredibly scientific in the way we go and do this continuous delivery of Kubernetes-based applications. So imagine you have a simple application, a few microservices. You know, it could have been sort of a monolithic legacy code, something super, super simple like a web app. For those of you who are familiar with it, there's the Docker cats versus dog app. So super simple application. It's a single web page. You go in, it gives you two buttons, cats and dogs, and you need to vote. And all it does is once you vote, it serves you the overall percentage of cats versus dogs that everyone voted for. Incredibly simple application. You can deploy it, obviously, sort of if it was legacy, you know, let's say 5-10 years ago, you probably had this massive stack of code all sitting in one place, all serving not very scalable. If you wanted to scale, you likely just duplicate the whole thing. Today, we're trying to go cloud native, trying to be more distributed. You could have it as Docker wrote it in a 5-service containerized application. So you have your backend that actually needs to do the calculations. Maybe you have a simple Redis queue, you know, a database to store the results, something to serve them, and the workers that actually need to go through the serving. Super simple, right? How hard could it be to take a 5-service application and deploy it on Kubernetes? Well, you know, if this sat in a previous server, and now I need to go ahead and say, okay, well, the first thing I need to understand is how much resources am I allocating to this application, right? Asaf touched on sort of cost optimization and resource utilization. That's always the basic layer. I need to understand how much to even allocate to that. And most people over provision, right? If you don't know anything, well, let me just go ahead and get a giant cluster just to make sure I have enough nodes and CPU and memory. But I do need at the end of the day to specify some sort of memory CPU. On Kubernetes, there's resources, requests and limits, which make it even more complicated. Obviously, the number of replicas you want to have. But even once I'm done with my basic sort of resources, there are other parameters that I may or may not choose to tune. So in this example, if you're running one of these services on Java, I think Asaf had it on one of the slides, JVM heap size is one of the first things you might want to tune, right? If you've touched Java in the past, you may say, actually, I never want to tune that. That's just awful. But that's exactly the point. If you don't tune your JVM size, especially as you go from sort of a monolithic application to a microservices architecture, the chances of you deploying and having it be stable and deploy reliably the first time is minuscule. Add to that things like the queue size for your queue, the data parameters for your database, you're getting into millions of potential configurations for your applications. Now, you may say, well, you know what? I know my application perfectly, right? I know what these need to do. I've done this millions of times before. Well, first of all, today, as we're moving to this new cloud native mindset, I would say tuning these things may not be in the hands of your application developers. More and more companies now are moving to separate their DevOps and development teams. Whether or not that's the right thing to do is, we can spend a whole hour on that. But what is likely happening today is your DevOps team is inheriting an application. And what they hear is, go deploy this. So they go, they have no idea what any of the components are. They may have dabbled in some before, but they need to go ahead and guess at these parameters in order to get the application to deploy in the first place. So how do they do it? And again, I think Asaf touched on this before. Manual trial and error is likely the first thing they're going to go with, right? So I have a million possible configurations. I'm going to choose one and I'm going to try it. And I guarantee you the application is not going to deploy. So I'm going to go through logs. I'm going to try to debug what's going on. And I'm going to try to deploy again. I'll tweak one of them, right? I have 10 parameters. Each one of them has, 100 or 1,000 possible values. I'll tweak one. I'll tweak two. No human can really encompass millions of configurations in their head. And so the road to tuning is incredibly slow. So what you end up with is a frustrated DevOps team that takes, say, hours, maybe days, hopefully days. I can say I've seen places where it could take weeks to tune something. I've seen places that dedicate entire resources just for tuning of a particular parameter or set of parameters. But most importantly, at the end of the day, once you're done tuning your application, you're left with something which is likely suboptimal. There's no indication that once you're done with the process, your application is running in the way that you want it to run. Not only that, but if something changes, both in your cluster or in your application or in your business needs, the likelihood that the same configuration remains optimal is zero. So again, what do people do today? You have a few options. You can go with the defaults, right? I'll tell you, we've tried it ourselves when we first ventured into Kubernetes a while ago. We're trying to deploy Elasticsearch. Well, there's a Helm chart, and the Helm chart comes with defaults. Well, it may or may not deploy, right? The way they write the defaults is it works for most people, but it works okay. It doesn't work optimally. You can't get, one size fits all. The second thing you can try is, like I said, previous configurations. I know this, I've done this before. The previous configs may not work. We're in a completely new architecture right now. Not only that, your new team who's trying to deploy this, they have no clue what the previous configs meant or how they're getting there. What's likely going to happen is you'll just over provision and misconfigure your application. And then the third option, as I mentioned, is trial and error. That's what 99% of people we talk to are doing today when they're trying to get their applications up and running. Even with continuous optimization, if I have additions, new versions, I want to continuously tune my application. What they do is they'll just dedicate time to it. Say, okay, here's a team, they're going to sit for a week, try to get to these new parameter values. I challenge anyone to try to do trial and error with like 3 metrics at the same time. Try to tune both for your cost or your resources and your latency and your throughput, and try to keep all of that in your head, or keep it maybe on a notebook in some sort of experiment. So what do we think the future is? When you're trying to get your application up and running, the first thing you need to do is actually run what we call an experiment. And again, to touch on Asaf's point of adding things to this CI/CD CO pipeline, how do we get something new in the CO pipeline, in the CD CO pipeline that gets your applications optimal continuously? We suggest setting up what we call an experimentation or lab setting in your development environment where you can test these new configurations. So what we're talking about here is not sort of tweaking the parameters, even though that's definitely part of the process. Think of the initial setup of, I want to understand how my application even needs to behave in this new environment. Well, I can suggest candidate configurations, right? So again, even if I'm doing trial and error, I have a list of my parameters and I want to set certain values to them, and I'll try them in dev. And if they work, I can measure the performance. I can measure whether or not my application actually deployed, and I can go ahead and deploy that in production. Now that I've deployed in production, I can go back to my experimentation and say, okay, now I've learned something even more. I've learned about how my application behaves in production, right? and I can tailor my experimentation, I can tailor my lab to look as closely as possible to what happens in production. That kind of virtuous cycle, that kind of learning cycle is what's going to get you from sort of stumbling in the dark to getting to the right application configuration, from the start and continuously from there on. Now, obviously, there's one very important piece here that I'm not mentioning, which is the machine learning, right? We've talked about AI ops, and obviously, we're very much focused on machine learning at Carbon Relay. I would say one of our biggest strengths is the ability to marry the machine learning component with the engineering Kubernetes component that we deploy on. So why machine learning? If we go back and talk about these, just one arrow, these candidate configurations, we've talked before about doing this in a trial and error setting. Someone who may or may not know the application or may know it in a different setting may try to do this a certain way or try to guess at what these configurations are. And once they've deployed one, well, they need to start guessing, well, okay, where do I need to go next? So imagine look at the middle picture there. Imagine this is a very simple application. I only want to tune two things. I want to tune memory and CPU, and all I'm tuning for is throughput. I just want to get as many requests through my application as possible. So I'm looking for the highest peak. If you're a human, even if you're trying to tune only two parameters, basically what you're doing is you're walking through this landscape and you're trying to go up slopes to figure out, well, okay, let me get to the highest peak. But even once you got to a peak, and you know that no matter which direction you go, you're going down, basically any kind of new configuration that you try, you're only getting lower throughput. There's no visibility into what is the other peak, what is the global optimum. That's what our machine learning model allows you to do. Basically, the machine learning model sees the entirety of the world. And what it does is it samples specific experiments or trials that you've tried. It says, okay, I know points 1, 2, 3, 4, 5 for certain. And based on that, I'm going to construct my worldview. And I know what the optimal solution is at the moment. Once you've supplied it with a few more data points, so let's say I've ran a few more trials or I've run one in production, I can go ahead and update this worldview and get a new set of results. What it means is I don't have to wait hours or days or weeks to understand what the optimum is. I get it within minutes or hours at most. The goal of the machine learning model is to run things both efficiently and, I'm going to call this, scientifically. It doesn't need any kind of domain knowledge. It doesn't know anything about Kubernetes. All it knows is, here are numbers, here are trials, go ahead and find me the optimum. So that's what we do at Carbon Relay. We provide a platform where you can say, okay, here is my Kubernetes application. And we work completely natively in Kubernetes. Again, there's no code changes that you need in this case. All you have to provide is your own manifests and what it is you're trying to optimize. So are we optimizing for performance? Are we optimizing for cost? Performance means different things to different people. Like I said, it could be throughput, it could be latency, it could be uptime, anything that you want to optimize. And you can optimize for multiple at the same time. So there's no reason to say, I want the absolute best performance without understanding what the cost implications are going to be. So even here, you can see sort of tuning multiple metrics at the same time, and there's no limits to how many of those you can add. Once we have your definition, this experiment runs automatically. And so I mentioned before the need to automate, and I think Asaf touched on that as well. Big goal of AI ops and optimization in general is not to make this more manual. The goal is to be fast and automated and intelligent about it. Our platform combines a Kubernetes controller with a machine learning model that run through this continuous optimization process that ends with your optimal configuration. And to the point of integrating into the CO, the goal here is not to do a one and done. As Asaf mentioned before, these systems are continuously evolving. Since you can run these experiments in minutes, you can just keep running experiments in the background as your system evolves, as you're releasing new features. All these things happen continuously. One last thing about the future of optimization in general, and then I definitely want to leave time for people's questions. I think Asaf touched on that as well. In order to have a true continuous optimization and have the right set of optimization tools, you have to inject some machine learning into the process. The old ways of the past of doing this manually and relying sort of on expertise is no longer the way of the future. We definitely need the experts who understand Kubernetes, who understand how these applications behave, but we have to add the machine learning component on top of that to help developers and to help the DevOps community to go ahead and be more efficient and focus on the problems that they are looking to solve. Thank you very much.
Thank you, Ofer. That was really helpful. To all the attendees, please feel free to enter your questions in the Q&A module now, and we'll take those questions. And to start, do either of you have questions maybe for each other, just while we allow some of the questions to come in, or feedback based on each other's presentations? Quiet group. Do either of you have questions for each other, just to get the ball rolling?
Yeah, Seth, we can talk a bit about JVM tuning actually. Oh, wait, there's, oh.
Great, so we have one. What is the required management overhead?
Oh, Tom, I guess you're asking me that. So what do you mean by required management overhead?
I think what Tom means is that some people could be sort of taken aback by the amount of adding or the amount of effort it would require, not just implementing and integrating a new system, but over time, what it could add.
Yeah. Oh, from like you're saying like a long running perspective. So there's no actual management overhead in the sense. What we're aiming for is continuous, like applying your new manifest continuously, right? So you can imagine I have a long running experiment, and all I want to do is just say, pick something for me, right? So if this is a single metric, I would say, I always know what the optimal configuration is, right? So I don't need the user to choose anything. If it's multiple metrics, there's definitely some element of choice there that you could have if you wanted to. Basically, if you're trying to balance between cost and performance, you should have the ability to choose. But what we offer is, if you don't want that, if you want a fully automated system, you can just go ahead and we will recommend what the right balance is for you and just deploy it.
Yeah, so I think you're also right that if we talk about the overhead of a CI/CD process, there's not much difference if we're adding another stage that's automatically optimizing. I don't think people tweak or log into their Circle CI to change a lot of things because they break, but rather because they want to utilize that for new things. They want to experiment more. So I think I absolutely agree with that.
Wonderful. We have another question. What is the required management overhead? And what are some of the benefits and size of cost reduction if I've already implemented solutions like moving to a spot preemptible instances?
So
I think,
oh, go ahead.
So I think it's orthogonal to utilizing spot or preemptible. So if you look at utilizing spot or preemptible machines, they're basically lower cost versions of the same machines that you're already using. And when you talk about integrating a new continuous optimization solution or real-time continuous optimization solution or anywhere else, it's about making or producing a lot more with your current infrastructure. So if you had a machine and now it's at a lower cost, you should still see huge gains in tens of percentages just by utilizing it with the right configuration or the right resource allocation, and so on. So you'll basically be using a lot less machines. It doesn't matter if they're low cost or higher cost.
Ofer, did you have a thought there too? I know you had said something originally.
Oh, no. I mean, that pretty much covers. I mean, at the end of the day, the interesting thing with cost reduction, I think in general, we like to highlight that as something that we do. I personally believe that there's a lot to do sort of outside of cost reduction, but the interesting thing with cost specifically is, like Asaf said, first of all, most people who are currently deploying, if someone comes up and says, you know, I know exactly what I'm doing, I've measured everything, or we've drilled down our costs to a T, that's just not happening, especially in the sort of shifting environments. So I would say there are huge benefits in understanding how your cloud architecture and cloud deployment should be planned. Outside of cost, like cost is a huge benefit of that, but you need to understand why you're deploying things a certain way in the first place.
Well said. Another question for both of you. How does Red Sky Ops perform against out-of-the-box configurations, Helm charts, etc.?
I'm not sure it's for the both of us, Ofer. I think that's yours.
Asaf, if you can answer, you can take that. It'll be amazing. So I've talked a bit about Helm charts before, and this was actually the first test that we did when we just started this. We're like, okay, let's see how well we can compete with Helm charts. And so to answer the question, you can immediately see a cost reduction, right? Like if you're talking about resource utilization, right? You can immediately slash costs. So, you know, we have, I think I briefly showed sort of what the results look like. You have something called the Pareto front, which shows you, if you have multiple metrics, it shows you what the optimal configurations are and what the trade-off is between multiple metrics. The defaults usually lie somewhere in the middle of the optimization space. So it's not great on either. It's sort of, you know, somewhere in the middle, like middle of the road. Like I said, it fits, it's sort of okay for everyone. But I would say beyond just being better at performance optimization and cost optimization, one big thing with the defaults is people tend to ignore them. I mean, most Helm charts won't actually tell you like all the defaults that are sort of under the covers. If you have deployment issues, that may be in the defaults as well, right? And it's not just whether or not you can slash costs by 30% or 50%, or you can bump your performance 2 or 3 or 4x. You won't even be able to deploy, depending on your architecture.
Great, thank you. We'll allow just a few more minutes for people to answer and type in some questions. Otherwise, we'll give you a few minutes back in your day. All right, you're taking me up on it. Well, thank you both for an amazing presentation. Really appreciate you taking the time. And thank you everyone who attended this webinar today. As I mentioned before, we will be sharing an email shortly with a recording and some additional resources. So keep a lookout for that. And enjoy the rest of your day, everyone.
Thank you very much.
Thank you so much.